Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on February 3rd, 2026, about 6 days ago. It identifies a key mechanism called latent tokens that explains why diffusion models excel at planning and shows that adding this mechanism to standard autoregressive models boosts their accuracy on Sudoku puzzles from around 27% to over 78%. The paper is titled Reasoning with Latent Tokens in Diffusion Language Models. And as we'll see later, the implications for improving model reasoning without massive retraining are really impressive. So Figure 1 visualizes this exact phenomenon using the Sudoku task. The chart plots accuracy on the vertical axis against the number of latent tokens on the horizontal axis. First, notice the blue curve representing diffusion models. It starts high, but adding more latent tokens steadily pushes accuracy from about 75% to nearly 90%. The real story, though, is the orange line for autoregressive models. Standard models start way down at roughly 27%, but once they utilize latent tokens through the multi-token prediction method, their accuracy skyrockets to nearly 80%, showing just how critical this mechanism is for reasoning. Alright, Figure 2 breaks down the mechanism behind this performance difference. On the left, the standard masked diffusion model uses bidirectional attention. When predicting the target token in red, it simultaneously attends to all other masked tokens, shown in orange, which allows it to reason jointly about the entire sequence. Conversely, the right side shows the semi-independent and semi-causal models. Here, the future masked tokens are grayed out and omitted from the forward pass. This makes generation much faster because it skips those calculations, but it sacrifices the global coherence that comes from looking ahead. Well, Figure 2 just showed us the structural difference, and now Table 1 quantifies the performance impact. It compares accuracy and inference cost across 3 reasoning tasks: Sudoku, Zebra, and Countdown. In the first row, the standard masked diffusion model achieves about 80% accuracy on Sudoku with a normalized cost of 1. But in the second row, the semi-independent diffusion model, which removes those latent connections, drops to 68%. Although this cuts inference costs nearly in half, the sharp decline in accuracy confirms that joint reasoning over latent tokens is essential. Okay, while the previous table compared just the endpoints, Figure 4 plots the full spectrum of performance. These 4 panels track accuracy across reasoning tasks like Sudoku and Zebra puzzles as we increase the latent token count. In the top left chart for Sudoku generation, for instance, you can clearly see the curve rising from the square marker at 0 latent tokens up toward the triangle marker, which represents the full model. This trend generally holds across the tasks, confirming that adding more latent tokens consistently unlocks better reasoning capabilities. So, while Figure 4 proved that more tokens aid reasoning, Figure 6 details the architecture that enables this in autoregressive models. On the left, the standard ARM is limited by causal attention, looking only at past inputs to predict the next step. However, the ARMTP design on the right replaces this with bidirectional attention. It lets the model attend to future masked placeholders, seen here in orange, so it can jointly predict multiple future tokens, which acts as the necessary look-ahead mechanism. Alright, Figure 6 outlined the method, and now Table 3 proves it works in practice. The first 2 rows compare standard autoregressive models against the multi-token prediction version. On the Sudoku tasks, accuracy leaps from just 27% and 5% all the way up to 78 and 53%. That is a massive gain. Crucially, the new method even beats the masked diffusion model, with uniform decoding in the third row, although the optimized diffusion model at the bottom remains the strongest overall. Well, Table 3 confirmed the accuracy boost, but Figure 7 investigates the mechanism by plotting loss against the number of latent tokens. The blue line for ARMTP slopes downward, showing that performance improves steadily as we add more latent tokens, eventually approaching the red square of the masked diffusion model. In contrast, the orange dashed line tracks the ablation model, ARNTP. This version has the same extra tokens, but lacks the multi-token prediction objective, and its loss actually increases, which proves that simply adding capacity isn't enough. The model must be explicitly trained to predict those future tokens. So, wrapping up, 2 takeaways stand out. Latent tokens are a general mechanism for reasoning, effectively bridging the gap between diffusion and autoregressive models. They provide a tunable knob to trade inference computation for sample quality, enabling standard models to handle complex planning tasks far better than before. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.